So inside of the word linear, like I kind of said, you see the word line. Line is part of that. That is no coincidence. A linear function, when graphed, is going to look like a line. It could look like that. Sometimes you'll see arrows drawn. You really should be seeing them to imply that it goes on forever and ever in each direction. So that's what's going to be the focus of today. Now, we've already seen one variable equations, something that just involves something like x. 3x plus 7 equals 14, and then you could solve that. 4 minus 2x equals 6. Things like that only have one variable. But now what we're going to see with linear equations in two variables is exactly that. There are going to be two variables, both x and y. Linear equations in two variables. And that's going to be the big distinction. So when we were graphing things earlier, you would see just a single number line. A single number line, you might see a point graphed on it like, hey, look, here's the point 3. But there was just one number line, so only one variable was under consideration. This could literally translate to the equation x equals 3. Well, now what happens whenever you bring multiple variables into it? Multiple variables. Well, you need a number line for each variable, technically. And so we could do this. We could say, okay, look, we've got two different variables, and now to differentiate between the variables, we will call this the number line for the x variable. We'll call this the number line for the y variable. That's a good idea, perhaps, but we'd like them to be all together on the same graph. So I could just superimpose them on top of each other. That looks bad, doesn't it? That looks downright terrible. So here's what we're going to do instead. Let's see if it'll let me just rotate. It doesn't like that. Yeah. So instead of putting one on top of each other like that, we're going to rotate our y number line 90 degrees, and then we can put them on top of each other like this. And now this will be our y number line. And actually this works out perfectly because they're not jumbling all over each other. In fact, this is going to be called the Cartesian coordinate system. That's all it is. Now what we'll do, we can put some fairly specific way markers along in each direction. Like so. And then we can start graphing points. The way the points will work is everything on this side of the number line over here. These are all positive. So this is your positive numbers on the x-axis. Over here then are your negative numbers. These are all your negative numbers on the x-axis. Along the y-axis, where are your positive numbers? Above or below? Above, for sure. So here's all your positive numbers on the y-axis. And so all your negative numbers are below. That's how these points work. So what we're going to do is we're going to be writing coordinate pairs. X comma y. You always put your x coordinate first and your y coordinate second. X coordinate first, y coordinate second. So for instance, let's get rid of all this. For instance, if you wanted to graph the point 3, 2, well, you would your x coordinates first. So you count 1, 2, 3 units in the positive x direction, positive 2 units up in the y direction. And so boom, there's your point 3, 2. If your point was to graph -4, -1, now your x coordinate, the first one is -4. You need to go 4 units to the left. 1, 2, 3, 4. And then -1 is the y coordinate, so you go down 1 unit. And so here's the coordinate -4, -1. So we can graph a whole lot of points. That's going to be something that we are going to concern ourselves with today. And then maybe the last thing to keep in mind real quick, we divide the Cartesian coordinate system into what we call quadrants, because as you can see, there's 1, 2, 3, 4 kind of distinct spaces on the graph, distinct areas, I should say. So we'll call this quadrant 1. We'll call this quadrant 2. We use Roman numerals. You start in the top right and you go counterclockwise. This can be quadrant 3. And this can be quadrant 4 down here. In quadrant 1, now quadrant 1 does not include the axes. You can't be on the line itself. That's not considered part of the quadrant. Your x coordinates will be positive. Your y coordinates will be positive. In quadrant 2, your x coordinates will be negative, but your y coordinates are still positive. In quadrant 3, both your x and y coordinates are negative. In quadrant 4, your x coordinates are positive, your y coordinates are negative. And that's pretty much all there is to it, the Cartesian coordinate system. Now we're going to be using this a lot today. What we're going to find out is that whenever we graph an equation, all we're doing is graphing every x, y coordinate pair that can be substituted in for the variables x and y in the equation. We're just graphing all those points at the same time and kind of connecting the dots, if you will, and creating the smooth whatever that comes out of it. In the case of linear equations with two variables, x and y, and there's nothing fancy. It's not x squared. It's not square root of y. It's just x, y, and then some number coefficients. Those are going to create linear functions. Those are going to create lines whenever we graph them on this lovely Cartesian coordinate system. As a little bonus, the system is named after René Descartes, a very famous French mathematician, but also he was more known for being a philosopher. He was a philosopher. And he formulated a lot of interesting ideas in philosophy, one of them being that we can reason about the natural world around us without having to observe it necessarily, without having to base it on empirical information and data. And whether or not that's true, it is a very interesting idea, and it's one that has had a major, major effect. He wasn't the first to formulate it, but it's had a major effect on the way we reason around the world. There's people who'd completely disagree with him. The entire field of statistics would probably disagree with that line of thought to some extent. So interesting. So all that, we're going to get back to linear equations that are in two variables. You're going to have both x and y in your equation. If you don't, you're talking about something a little bit different. Now, it can still be graphed in a two-coordinate system, but you primarily want to have an x and a y. And they're going to create straight lines. A, B, and C are all going to be numbers. They have to be. Those are just considered the coefficients of the equation. So some examples of this. Here's a one variable equation. This is just one variable equation. All you have is x. It is still linear because x is just x to the first power. Remember, secretly it has a power of 1 up there, even though it's not written. It's not squared, it's not to the 5th power, it's not the square root, it's just good old x to the first, and then everything else behaves a certain way. They're just constants at the end of the day. They're just numbers. So this is considered a linear equation, but it's only one variable. Now, we're going to have a two variable equation. So we have both x and y. This is a two variable equation. It is still linear because both x and y just have a 1 power, a power that's the first. Even though it's not written, it's implied. That is pretty much the standard for what makes it linear. You can have linear equations in 17 variables, as long as each of the variables is just raised to the first power. That's how it works. Now we're going to see some interesting ideas. Let's zoom in on this one a little bit. I'll erase the first powers because they're implied. If they're not written, it's implied to be a first power. Let's consider the point about -2, 4. Let's consider the point -2, 4. Okay, well, what we're going to do is we're going to ask, is the point -2, 4 a point on the graph here? That is, if I plug x equals -2 into the equation and y equals 4 into the equation, does it create a true statement? That's what it means to be a point on the graph of an equation. It just means that your variables, when you substitute those specific values in, you create a true statement out of the equation. Well, let's find out. We'll do 4 times, we're plugging -2 in for x, minus 6 times, we're plugging a +4 in for y. Screwed up. And then we're saying it's equal to 5, but really we're asking, is it equal to 5? If it is, then yes. Well, you work out the math, you're going to figure out pretty quickly that's not the case. -8 minus 24, is that equal to negative or +5? Not on your left. You get -32 on the left. Is not equal to 5, no. So this creates a false equation or a false statement. Thus, -2, 4 is not a point on the graph of the equation. You could even say -2, 4 is not a solution to the equation. That's another way to put it. It's only a solution if you can plug in the specific values for your variables and get a true statement out of it. That's entirely what it means to be the solution to an equation. Graphing then, I'll reiterate, graphing an equation is nothing more than drawing the picture of all the possible solutions to the equation, all on one big graph. That's all it is. That's all it is. So what we're going to do is we want to graph these things. When you have it written in this form, this is sometimes called the standard form of a linear equation. It's something times x plus or perhaps minus something times y equals some constant. One way to graph the thing is to look for where does it cross the x-axis. That's called the x-intercept. And where does it cross the y-axis? That's called the y-intercept. So the x-intercept, that's going to have a y value of 0, pretty much by definition. Because when you cross the x-axis, your y value is 0. And vice versa. The y-intercept, where you cross the y-axis, will have an x value of 0. So let's look at this guy. 3x plus 2y equals 6. We're going to graph 3x plus 2y equals 6. All right, let's figure out the intercepts. This occurs when y is equal to 0. So you do 3x plus 2 times, in this case, you plug a 0 in for y. And then you solve for x. 2 times 0 is 0, so this just becomes 3x equals 6. Now we need to brandish our equation solving skills. Divide both sides by 3. You're going to get x equals 2. The x-intercept then, we got an x-coordinate of 2. What's the y-coordinate? 0, exactly. An x-coordinate of 2, we plugged y equals 0 in, so that's automatically going to be the y-coordinate. And so when we graph it, we'll deal with it at that time. Now let's find the y-intercept, and this occurs when x is equal to 0, and we solve for y. So we're going to plug a 0 in for x. We're going to let y be y. We're going to solve for y, basically. Divide both sides by 2. And you'll end up with y equals 3. So now the y-intercept, well, the y-coordinate will be the 3. What will the x-coordinate be? 0, exactly. So my y-intercept is not 3. The x-intercept is not 2. The y-intercept is not 3. That's not how that works. The x-intercept is exactly what I labeled here. The x-intercept is the coordinate 2, 0. Do not make that mistake. The y-intercept is the coordinate 0, 3. But now we can graph the line. We need to make an x and y coordinate system. I won't draw out every divot point on there. The x-intercept is 2, 0, so on maybe right here is my x-intercept. My y-intercept is 0, 3, so maybe the y-intercept is something like this. And what do you think I do with those 2 points? Connect them, that's right. Draw the line that goes in between them. That crosses through them, but then continues on infinitely. Oops. So about like that. We'll draw arrowheads on both ends, implying that the line continues on forever and ever. And this is how we graph with intercepts. In most cases, you can graph with intercepts unless it just so happens that the line crosses through the origin here, the center point, because then the x and y intercept are both 0, 0, and you don't have a second point to go off of. So you're gonna have to do something a little more crafty in that particular case. But that's graphing by the intercepts. You can see they got basically the same thing. So here's the skinny. If you look at the line we just graphed in orange here, you'll notice that as I go from left to right, the thing is going downhill, isn't it? It looks like I'm walking downhill. Whenever you're walking downhill, you're said to have a negative slope. So this is a negatively sloping line because it's going downhill from left to right. If it were going uphill, you'd have what kind of slope? Positive, yeah, you'd expect that. So here's how it's going to work. We're going to learn about the 4 types of slope. Slope measures how steep your line is and what its orientation is. That is it going uphill or downhill? So 4 types of slope. So let me draw 4 distinct graphs. So your most basic kind of slope, it can look like this. It can even be really steep, or it can be pretty mild. But the point is, if you go from left to right and the thing is on an uphill trajectory, you're talking about positive slope. And when I say positive slope, what we're going to do is we're going to define the slope in just a moment as an actual number. And I mean the number is literally positive. So this will be positive slope. The value you place on the slope, the number itself, is a positive number. Over here, if your slope's downhill, I mean, it can be going steeply downhill. But if your general shape is that it's falling, then you're going to be talking about negative slope. I mean, the value of the slope is literally a negative number. What are some other shapes you could make if you wanted to? Straight up and down, or? Yeah, straight left to right, horizontal. That's exactly right. So you can. Exactly. So what we're talking about the form of the equation has to just have an x to the first power and a y to the first power, even if you move it all around on the equation. The second you start trying to put exponents on your variables, things completely change. Yeah. And you just study each of the different ways it can change and what it means. If you have this, a nice flat horizontal line, that's zero slope. And I mean the number 0. If you asked me the slope of that line, I would say it is the number 0. And then finally, if you had this funky case where you had straight up and down vertical slope, or a vertical line, I should say. Well, this one's a little bit tougher. It's kind of the idea. If you have vertical slope or a vertical line, that's said to have undefined slope. And what I mean is, if you ask me what the slope is, hey, what's the slope? What's the number for it? I'm going to say there isn't one. It is undefined. It does not have a number. Theoretically, one might think that the number for the slope here is actually infinity, and that could be argued, but that's not exactly a number. Not in the sense that we usually imply. Yes, sure. Uh-huh. No, that's a great question. So she asked, so these are the 4 kinds of slopes. She's talking about parabolas. I'm gonna have to freehand this one. Maybe like that. This is called a parabola shape. This will occur when your equation in some way involves x squared. This is the more general form of it. And the rest of the equation behaves in a certain way. This has curvature to it. What we're inherently dealing with, lines have no curvature. They're straight. They're completely straight up and down, or just left and right, whatever. So again, I mean, you can get all kinds of funky. The good news for you is we're not even going to be dealing with parabolas and the quadratic equations like this. We will just leave that off the table for this 0332 course, and we won't investigate it in 1332. So how many of you are planning or have already taken college algebra? Is anyone thinking about taking that? I would strongly suggest you look at your degree plan and see if you actually need college algebra, or if they're cool with you taking 1332, which will be the second half of this semester, and if you need a second math class, taking 1342, which is a statistics course. And the reason I say that is that college algebra is just very abstract. You go into an absurd level of detail on things like graphs, real heavy. That's a much more heavy-hitting math subject, to be honest. What we're learning here so far is kind of a survey of math. In 1332, we're going to learn some weird math things that you may not even know were considered math, but it's not quite like as difficult, frankly, as graphing, equations, dividing polynomials. That's the kind of stuff you need if you plan to go higher on in mathematics. Math 1314 is college algebra. And unless you're absolutely sure you need it, you do need it for sure. Well, I mean, it's a very doable class. It's just that you're going to be spending a lot of time with it. That's just the honest truth of it. And some degree programs do require the college algebra. I think it's just to make it harder. It's literally just to force you to work harder because it is a tougher class. I mean, I'm being straight up with you right now. I don't believe in lying to people and BSing them. So, anywho, if we go all the way back, we can get back our previous. There it is. Beautiful. So the 4 basic types of slope. These are all that we're going to deal with. But it's good to know when you'll have what. Now let's look more specifically at the slope. What exactly is it? There's a couple different ways to define it. One of the most popular ways to define it is called rise over run, meaning it is a ratio of how much the thing changes, your line changes in the vertical direction for every change in the horizontal direction. That is a pretty common interpretation of it. The steeper your line is, the larger the value of the slope will be in absolute value terms. So this line is pretty normal steepness, and it's positive. You can tell this line is positive. But if I were to make it a lot steeper like this, it's still a positively sloped line, and the slope would literally be a larger number. If the slope here was like 2, the slope here would be like 5. So rise over run, that's the common interpretation. Of slope. There's a couple ways even to interpret that. Let's look at a couple different slopes. And I'll say this, we'll use m, a lowercase m, to represent slope. Let's say you're talking about m equals 3. You have a slope of 3. Is 3 positive or negative? Clearly positive. If you don't have a sign, it's automatically positive. If you do have a sign, it's probably going to be a negative sign in most cases. So clearly it's positive 3. Now we want to use the rise over run interpretation of positive 3 here. So even though is 3 a fraction right now? Perfect. You're absolutely right. We can very, very easily, almost arbitrarily, say it's the same as the fraction 3 over 1, just for the purposes of using rise over run and interpreting it in that vein. So what this means, the rise is always on top. The rise is telling you your vertical change. The run, you think about running, you'd like to run on a straight line path, a horizontal path. The run is telling you your horizontal change. Put another way, vertical, always going to be on top in slope over horizontal. What this means then, for every 1 unit I run to the right, and I use 1 because that's the denominator. The line rises 3 units, the top number. Let's see what this looks like on a graph. We'll kind of zoom in on the first quadrant of the graph. That's going to be a fairly steep line. And what this is going to mean is that for every, and it's a little tough to draw, I'll admit, I'll use red. For every 1 unit I go to the right, that's 1 unit. This thing rises, it goes up 3 units. And I know it's rising because the slope is positive. So from left to right, it's on an upward trajectory. So we have the basic interpretation. Let's look at a couple different ways we can mess that up a little bit. Well, what if I changed the 1 on bottom to a 4? And now suddenly my slope is now 3/4, 0.75. It's still positive, so the thing is still on an upward trajectory, but I've actually made the slope smaller. I went from a value of 3 down to the value of 3/4, which is about 0.75. So suddenly the line is not going to be as steep as it was before, not nearly as steep. Maybe something like that. But the interpretation is going to be the same. The number on bottom is my run. It's a positive number, so it's going to be always rising. So the line rises 3 units for every run of 4 units. Every time I go to the right 4 units, the line is going to go up 3 units. And so it may not be very well to scale, but that's okay. For every 4 units it goes to the right, it's going to go up 3 units. You can see why the slope then is a good measure of the steepness of the line. It's almost just clearly from definition. Well, rise over run is used because rise and run both start with R, so it's easy to remember, rise over run. It's just like a cute little mnemonic device for our memories. But if the slope is negative, it's not really rising, is it, as you go from left to right? It's more like falling. So you just have to keep that in mind. So let's look at the case for negative slope. Let's look at what happens. Let's say you had a slope of -2. -2, does that look like it's a fraction? No, so what do I put it over? Just put it over 1. Just so your rise over run becomes obvious. Now, we'll draw our line. Since the slope's negative, it's got to be going down like that, doesn't it? So that's certainly going to be the case. And now calling it rise over run, it's probably better to call it fall over run. But we're not going to worry about that. We're still going to talk about the run going to the right. And now we're just going to talk about the vertical change. Now what this means is for every run of 1 unit, the bottom number, the line doesn't rise anymore, it falls 2 units because it's negative and 2 is the number on top. In other words, it does something like this. Every 1 unit you go to the right, now it falls, it goes down 2 units. Yes? What do you mean exactly? Uh-huh. Ah. Uh-huh. Great question. The only reason I zoomed in on the first quadrant was for simplicity's sake, especially so we could zoom in and really see. What's that? Exactly. So what you're saying is, let me see if I understand what you mean. We could move this line anywhere, but it maintains the same slope? Exactly right. So you can have a line that goes anywhere you want, but it's the same line in spirit because it has the same slope. Yes, what we're going to see is that there's 2 elements we're going to focus on for the equation of a line. It's the slope of the line, but all the slope of the line does is tell you kind of its shape. We also need to know what its y-intercept will be, because once you know where it crosses the y-axis, you've anchored the line and you've forced it to stay at one place. Yep, so good question. So you can change the y-intercept, and that's going to change the position of the line, but not its spacing, shape, or anything. Good question. And then last but not least, one more quick example. What if you made it -2 over 5? Why is this not? Like that, it's still negative. So it's still going to be falling, but you've shrunken it in absolute value terms. So it's going to not be quite as steeply falling as before. And so with this line, what we can say, I mean, this one's going to be even more silly. For this one, for every one run now of 5 units, the bottom number of the line falls 2 units. So it's going to be every 5 units you go to the right, this thing falls 2 units. It goes down by that. So slope is a measure of the steepness of the line. It's everything. It's really everything. The y-intercept just anchors the line at a specific place. What we're going to find is that we can calculate the slope of a line that crosses through 2 points. Now, to keep it general, they'll just call the first point x1, y1. The first x coordinate, comma, the first y coordinate. They'll call the second point x2, y2, the second x coordinate, and the second y coordinate. So x1, y1, and x2, y2. To calculate that slope, it uses a simple formula. You take the difference in the y coordinates divided by the difference in the x coordinates, which makes sense because the y coordinates prescribe up and down motion. The x coordinates prescribe left and right motion. So the differences in the y's over the differences in the x is exactly rise over run. It's the change in your vertical motion divided by the change in your horizontal motion. So let's find the slope of the line passing through the points -3, -1, and -2, 4. So slope of the line crossing through, boy, my memory is really bad, -3, -1, and -2, 4. So whatever that line is, we could even draw it. You can just draw your Cartesian coordinate system, find -3, -1, find -2, 4, and draw the line connecting them. Well, here's what we're going to do. My slope formula, m, is going to be equal to y2 minus y1 over x2 minus x1. So what you do is whatever you want to call your first point, call it x1. Oh. x1 and then y1. It's always good to label. Don't think you're above little tricks like this that help you organize your thoughts. You are not. I am not above it. None of us are more special than using certain helpful tricks. Trust me. x1, y1, x2, y2. So be very careful. This is subtraction up here. Down here is also subtraction. We're going to subtract even if we end up subtracting a negative number. That's fine. Don't let it throw you off. This is going to become, well, y2 is 4, y1 is -1. So I'm doing 4 minus -1. Don't just do 4 minus 1. Do 4 minus -1 because that's exactly what it is. On bottom, x2 is -2 minus -3. And so you'll end up with 4 minus -1 becomes 4 plus 1. -2 minus -3 becomes actually -2 plus 3. And you get 5 on top. On bottom, you'll get 1. So you'll get a slope of +5. +5 is your slope. So whatever this line is, for every 1 unit I go to the right, the thing goes up 5 units. Which kind of makes sense. Here, the first point, the x-coordinate was -3. Here, the x-coordinate was -2. So I've only gone 1 unit to the right, from -3 to -2. but this thing has gone up 5 units in terms of y. It's gone from -1 to +4. So that's all it really is. So the slope of the line is 5. Slope-intercept form of the equation of a line. What we're going to do with this next time, tomorrow, we're going to rewrite the equation of a line in a more convenient manner. We're going to write it to where we can easily read off the slope of the line immediately, and we can very quickly figure out what the y-intercept of the line is as well. Once you have those two things determined, the slope kind of tells you the shape of the line, how it's slanted, if it's uphill, downhill. The y-intercept then anchors that line at a specific point. So let me take attendance. Don't go nowhere.